Welcome to the Explainer. Today, we're diving into a statistical puzzle that trips up even the pros, and we're drawing on some fantastic insights from StatHarbor Analytics to do it.
All right, let's just jump right in. You've probably been here before, right? You're running an analysis, you get a results, and then you think, let's adjust for age, or something like that. And bam, the numbers shift. So what gives? What's really going on?
So maybe your odds ratio goes from, say, 6.0 down to 4.5. Your first thought is probably, awesome, I just got rid of some confounding bias. And, that's what we're all taught to think. But it's not always the full picture. The real reason is, well, it's a bit more of a twist, and honestly, it's way more interesting. To really get to the bottom of this, we need to talk about a core idea in statistics. And our key concept for today is something called collapsibility.
Okay, so what on earth is that? Let's break it down. Basically, a measure is collapsible if the big picture lines up with all the little pictures. If the overall effect for everyone is just a nice, clean average of the effects you find in your subgroups, like for men and for women, for example.
Here's the thing, though. Not all stats are built the same. Some measures, like risk difference or relative risk, they play by the rules. They're collapsible. But others, and this includes the super common odds ratio and hazard ratio, have this weird mathematical property that makes them non-collapsible. And that's where our puzzle really starts. All right, let's make this real with a side-by-side comparison. This is where you're going to see what I'm talking about in action. We'll look at a collapsible measure, the risk ratio, and then a non-collapsible one, the odds ratio. So first up, the risk ratio. Look here. The risk ratio for men is 2.0. For women, also 2.0. So when we combine them and look at the total population, no surprises here, it's 2.0. See how clean that is?
The big picture perfectly matches the smaller pictures. This is textbook collapsibility. Everything just lines up, exactly how your intuition tells you it should.
But now, let's try this again, this time with the odds ratio. Okay, so for men, the odds ratio is 6.0. For women, it's also 6.0. So far, so good, right? The effect seems to be the same in both groups. But hold on. Look at the total. The combined odds ratio for the whole population drops to 4.5. Wait, what? Let that sink in. The effect is 6.0 in every single subgroup, but when we put them together, it becomes 4.5. And the critical part here is that we've set this up so there is zero confounding. This change has nothing to do with bias. This right here is non-collapsibility in action. It's not a mistake, it's not a paradox, it's a fundamental mathematical property of the odds ratio itself. So the big question is, why? Why on earth does the odds ratio do this? Well, like I said, it's not about bias, it's baked right into the math. It all comes down to something called nonlinearity. The math behind the odds ratio isn't a straight line, it's a curve. Think of it this way. If you average 2 points on a flat, straight ruler, the average is right there in the middle. Easy. But if you try to average 2 points on a curvy S-shaped road, the math gets weird. The average isn't where you'd expect it to be. And that's all this is. The odds of the average risk is not the same thing as the average of the individual odds. It's a funky property of the math, not a flaw in your data. And it's so important not to get this mixed up with Simpson's paradox. Simpson's paradox is when a trend reverses because of a hidden confounding variable. Non-collapsibility is totally different. It's a numerical change that can happen even in a perfect randomized trial where there's no confounding at all. Okay, so let's get down to brass tacks. What does all this mathy stuff actually mean for you when you're reading a paper or doing your own work?
Well, this little quirk leads to two huge mistakes people make all the time. First is the bias fallacy. You see that odds ratio change after you adjust for something, and you immediately think, aha, confounding, when really it might just be the math doing its thing. Then there's the comparison fallacy, and this one's really dangerous. It's when you try to compare an odds ratio from one study that adjusted for, say, age with another that didn't. You can't do that. You're literally comparing apples and oranges.
So what's the right way to think about this? Simple. First, know what kind of measure you're using. Second, if it's an odds ratio, just expect it to change when you adjust for things. And third, and this is the big one, be crystal clear about what you're reporting. Are you talking about a marginal effect for the whole population or a conditional effect for a specific subgroup? And this really gets to the heart of it, a point that StatHarbor Analytics makes so well. You have to be clear. Are you describing the average effect across everyone or the effect for a specific kind of person within your study? Because for non-collapsible measures like the odds ratio, those are two very different questions with two potentially very different answers. So I want to leave you with this one challenge. The very next time you're looking at a study or running your own analysis and you see an odds ratio, just stop for a second. Ask yourself that one simple question. Is this effect marginal or is it conditional? Just knowing to ask that will completely change how you interpret the results. It's a total game changer.
We really hope this explainer, brought to you by Stat Harbor Analytics, helps you tackle your own data with a bit more confidence.
If you found this useful and it resonated with you, do us a favor and subscribe. And make sure you hit that notification button so you don't miss our next deep dive. Thanks for watching.